In this video, we want to find out what the zeroth homology has to say about a topological space. And the statement is pretty easy. Since we have now defined homology also with coefficients, let me state it in the most general version right away. And the statement is the zeroth singular homology of any topological space X with coefficients in some commutative ring R is isomorphic to the direct sum of one copy of R, of the R module R, for each path component of X. So remember, we used the notation pi 0 to denote the set of path components of X. Okay, so in other words, by the rank, the rank of this free R module here, we find the number of path components of a space. Okay? So this is the information the zeroth homology provides, the number of path components. So let's prove this. Well, last time I told you about the additivity axiom which singular homology satisfies. That was the statement that actually the singular homology, no matter of what degree, preserves the coproduct decomposition of the space into path components. So that means basically everything that needs to be done now is to see that the zeroth homology of a path-connected non-empty space is isomorphic to R. So by additivity, meaning by the additivity axiom, it only remains to show that the zeroth singular homology of X with coefficients in R is isomorphic to R in case, so if X is path connected. Okay. If X is path connected and non-empty, like I said. So if X is path connected and non-empty. Yeah, because we already know that the homology of an empty space is just trivial in all degrees. Right. So this is what we want to assume now. X is path connected and non-empty. And to see that then the homology is just R, we now introduce a certain homomorphism. So let's write this as a definition. This homomorphism is called the augmentation homomorphism. Okay. And that is the following homomorphism. It's usually denoted by epsilon, so let's write epsilon. And it starts at the zeroth singular homology of X with coefficient in R. And its target is just the ring R itself. Yeah? Or if you want, the R module R itself. Yeah, it's a homomorphism of R modules. And how's it defined? Well, a singular zero chain is nothing but a formal linear combination of singular zero simplices, so basically points in the space. So let's take such an element, some I, Ri, sigma I. So such a formal linear combination of zero simplices, which we index by I, and the coefficients now come from the ring R. Yeah? And such an element is just mapped to the sum of the coefficients. So we just map it to the sum of the coefficients within the ring R. Yeah? And of course, linear combination again means that here this is a finite linear combination so that the sum is defined. Okay, so this is a convenient homomorphism which can be used to slightly alter the singular chain complex. Yeah? So usually after the zeros singular chain module, the next term is just 0. But instead, one could also say, okay, we augment the chain complex by going from C0 to another R module R here, like this one, by this precise augmentation homomorphism. This gives a chain complex again, so still the composition of two arrows is always 0. But this has now the additional property that it's exact at 0. Yeah? This augmented chain complex, and this is precisely the assertion that we need now. So let me formulate this as a claim. The claim is that the kernel of epsilon is equal to the image of the first singular chain boundary homomorphism. Yeah? So this is precisely what exactness should mean for the augmented chain complex, exactness at 0. Okay, and now I say this is precisely what we need to prove here. So why is that? So why are we done when we have proven this claim? And that's because in that case, let me just write this in parentheses, then we have the following calculation. Well, the 0th singular homology of X with coefficients in R. What is this by definition? Well, the 0 cycles, that's actually just C0 itself, because the 0th boundary is 0. So that's C0 sing XR. And now we mod out the zero boundaries, but the 0 boundaries, that's this image here, if this is the same as the kernel of epsilon, well, then I can mod out kernel epsilon here. And then we have this usual, what was the name? The first Noetherian theorem, I think, saying that, well, if we have a surjective homomorphism of R modules like this one, I mean, this is apparently surjective, yeah, I mean, you can just take one 0 simplex and write any coefficient in front of it. This will produce any element in the ring you want here. And if you have such a surjective homomorphism, then all you need to do is mod out the kernel, and then this domain space mod out kernel will be isomorphic to the target space R here. Yeah? So if the claim is proven, then this will just be isomorphic to R, and this is precisely what we need and what we want. Right? So all that's left to be done is to show this claim. And this claim asserts an equality of two, well, submodules. So typically such an equality is proven by proving both inclusions. So let's start with the first one. Which one is the easier one? I think this one is the easier one. If we take the image of the boundary operator that's included in the kernel of epsilon. So why is that true? So we take an element in the image, or let's first of all be even lazier and take a particular element in the image. So we just take D1 of one particular singular one simplex. Yeah? So this would be typical, or this would be one element in the image. And we evaluate this now in epsilon and see what comes out here. Well, how was the boundary operator defined? We have to restrict the simplex to the one I get when I omit the 0th and the first variable. So, and the omitting index is the one that rules the sign. So this should be sigma 1 restricted to V1 with a plus sign, and then sigma 1 restricted to V0 with a minus sign here. Yeah, because here we left out the first vertex, which produces the minus sign. Yeah, should be right like this. And, well, what is this? So let's remember the definition. This augmentation homomorphism, it just adds up the coefficients of this singular 0 chain here. And, well, we have a coefficient +1 here and a coefficient -1 here. Yeah? So a ring in our definition always contains a unit. Yeah? So this is just 1 minus 1. Which is 0. Somehow the pen doesn't really detect my writing here. Okay. So now we've shown that, well, the image of one such singular simplex goes to 0 by applying epsilon, but of course this whole calculation is linear, yeah? So if I take here just a linear combination of one simplices, then I can pull out the sum and all the summands will be 0, and again I'll get 0 here, yeah? So the image of every singular one chain is mapped to 0 by epsilon. Okay, that's the first inclusion. Now let's proceed to the other one. Why is the kernel of epsilon contained in the image of D1? Yeah, let me remind myself why. Okay, so, well, let's just suppose we're given an element in the kernel. This is how we should start. So suppose we have the relation that epsilon maps some singular 0 chain to 0. So let's write here sum I Ri sigma naught I. Let's assume that this is 0. Well, what does this mean by definition of the augmentation homomorphism? It means that this coefficient sum is 0. All right, and from knowing that the coefficients of our 0 chain here satisfies this condition, that the sum is 0, we now have to produce a singular one chain of which this 0 chain is a boundary. So how do we do this? Well, we do something that we already did earlier in the course on the fundamental groupoid, I think. We just pick now paths from a fixed base point in the space to any other point. Yeah. So in particular, maybe not to any other point, but actually to the points that are given by these 0 simplices here. And this is what we do. So fix some base point x0 in x. Yeah, and actually, up to now, this was all formal computation. I mean, if we want to prove this theorem, at some point we need to use all the prerequisites we have. And here is one we use. I mean, we can only fix a base point because we assumed that the space X was non-empty. Yeah? So this enters at this point. So we fix such a base point, and then we need to use, of course, our second assumption, namely that X is a path-connected space. And this is what we use now. Namely, by path connectedness, we can connect every X, we can connect the base point X0 to every point given by such a singular 0 simplex here. And this is what we do now. So fix x0 in x and pick paths. How do I want to call them? Gamma I, I guess. Yes. Gamma I in x with the property that those paths initiate in x0 and end in, well, the point that's given by the simplex. So in other words, I just evaluate my singular 0 simplex at the only vertex I've got. Yeah, so this gives me a point in x. So by path connectedness, I can do that, right? And now how do I cook up a one chain from these paths? Well, this is not too far away now because a path basically is nothing else than a one simplex. Yeah? So we now view gamma I as a singular one simplex. Yeah, so this unit interval we canonically identify with the standard one simplex. So we view gamma I as a singular one simplex sigma 1 I starting at delta 1, yeah, which is just the same thing as I. Or it can be canonically identified with I should say. And this, of course, maps to x. Yeah? So in such a way, all those paths can be interpreted as singular one simplices. And now I claim that simply the sum of all those singular one simplices with coefficients Ri will actually give us the given the desired pre-image of our given zero chain. So let's make that calculation. D1 sing of the following one chain. I just take some I, Ri, where these Ri are the coefficients from above, yeah? So the ones that were beforehand written in front of the zero simplices. And now I take my just constructed one simplices, sigma I1. Okay, let's do this calculation. So on the one hand, I have, well, again, the boundary of the one simplex that I get by omitting the zeroth vertex. So that gives me the plus sign. So this should be here, sigma I 1 restricted to V1. And on the other hand, I have now with a minus sign the sum I Ri sigma I1 restricted to the zero simplex I obtain by omitting the first vertex. Yeah? And now we make the following observation. So the paths were so chosen that they all started at the base point x0. Yeah? So this has the effect that this restricted simplex here, this zero simplex here, is the same for all I. Yeah? In other words, I can just pull it out here out of the sum distributively, and therefore I can write this coefficient sum just in front of it, but this by our assumption that the zero chain was from the kernel of epsilon is just zero. Yeah? So this was what we concluded up here, yeah, at this point. And therefore all that remains is the left summand here. And this one, well, what do we got there? There we got this one simplex sigma I restricted to V1. So this is sort of the, after identifying the simplex back to the path, this is the endpoint of that path. And this was precisely the given point of the ith singular zero simplex of the chain we started with. So long story short, this is just sigma 0 I. So we now see that this is precisely what we wanted. Yeah, we started with a singular zero chain. Where is it? Up here. This one here, which was in the kernel of epsilon. And now we produced a pre-image, namely this one here, under D1, yeah, which maps to this given element. So we showed that actually the other inclusion also holds. Kernel epsilon is contained in the image of D1, and therefore the proof is now complete. So let me draw the box.